This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
All right, we'll go over this stuff. So if you see that it has a if you know that it has a syn or anti mechanism, then you do cis, syn, or erythro. If you know that it has a carbocation or carbon radical mechanism, then it's just all four possibilities. So the first one with a Z and an anti mechanism would be 3O. Aha. Because it is a Z or cis configuration, not that those are interchangeable, but for purposes of this, they are. And syn is crossed out, so that means erythro has to also be crossed out. So that's your answer there. Because it's a radical mechanism, you don't use cis, syn, erythro, and besides that, you have one chirality center, so it doesn't matter what the mechanism even was. That's going to be the R and S combination. And E configuration and two chirality centers. A syn mechanism and two chirality centers means that you're doing cis, syn, erythro. And because you're crossing out cis to write E, but you're leaving syn, then that means that erythro becomes 3O. Since you're crossing out 2 or nothing. The first two are given to you, and so that tells you what you have to do. Any questions with any of those so far? All right. Carbocation mechanism and two chirality centers means that you can add from either side in the first step and from either side in the second step. So that's what's giving you the four possibilities. This one, I'm sorry, you didn't know. This one is a syn mechanism. I'll show that one to you today. But now that you know that little factoid, this has two chirality centers, which means the mechanism is important to get at the right answer. And so when you look at the mechanism and it's syn, then that's telling you using cis, syn, erythro. Oops, this. You start out Z and it's a syn mechanism, so it's an erythro product. And when I say erythro, it isn't just one product. It's a pair of erythro enantiomers. Unless the compound is meso. Two chirality centers, so the mechanism is important. That's the one where the mercury has an electron pair to bond to the developing carbocation, so you don't have to have a carbocation, so that makes the strained ring. That means that the next reaction has to occur from the opposite side, so that's anti. It's not a Z configuration in the original starting material, it's E. The mechanism isn't syn, it's anti. That crossed out 2 already, so you leave the erythro. Any questions? This one produces 2 chirality centers as a result of the reaction. So the mechanism is important. Hydrobromic acid with peroxide is going to create a radical mechanism. If it's a radical, you start out with trigonal planar vinylic carbons, and you have a trigonal planar radical that you can react with. And so that one is going to be all for possible stereochemistry configurations. The next one, you have 2 chirality centers. Then the mechanism is important to predict the stereochemistry of the reaction. This one has chlorine, would react in the first step because the hydrogens you would cross off, and so the pi bond electrons would react with the partial positive that's induced in the chlorine. Because you're reacting with the chlorine in the first step, and chlorine has non-bonded electron pairs, then that one is going to produce a strained ring. So that means that that's an anti-mechanism. Because it's anti, then you do cis and erythro. And you start out with a Z configuration in the alkene, so that's left the way it is, and then you have an anti-mechanism instead of a syn mechanism because you've crossed out one thing, you need to cross out a second. The only option is to change erythro to 3O. And the last one, you have 1 chirality center, so you don't even have to think about it. It's RNS. Okay, those of you who, when I went around and I said, how did it go? And you went, I don't know yet. Now what do you think? Kind of okay? Is there any particular kind of trouble spot for you?
I think I just forgot about the most.
Oh, okay. Okay. So I just got to get you practiced and used to thinking about that. It is kind of a new concept, so that makes sense. All right, then. I would like to try to finish up the chapter before you go to Thanksgiving break, so that all we have left in the 2 weeks after you come back is Chapter 8 and review, to kind of keep it a nice even pace for you. But let's see, I want to make sure that you can put all of this together before I introduce new concepts to you. So I'm wondering, starting on page 19, I think it is. Yeah, starting on page 19. Which ones of those did you already do? We'll pick up one that you haven't done yet. I think you did one on page 20, maybe, or no? You didn't do that one either? All right, then, we'll start there. Page 20. So this is going to walk you through step by step, incorporating all of the stuff that you've learned from all the chapters so far, and kind of help you see how to work with these problems when you have a strained ring as part of the reaction mechanism. So this one, you're reacting 2-methylbutanene with bromine in CH2Cl2. So CH2Cl2 is a solvent, and you notice that it's not water or an alcohol, so it's not a reactive solvent. The only reason it would be put in there would be to tell you specifically, oh yeah, by the way, this isn't in a reactive solvent. So if you see CH2Cl2, cross it off, it's not doing anything except for solubilizing the components. Another one that would be the same kind of thing would be CCl4, or if you see alphabet soup, like THF or DMSO or something like that. All of those are solvents that you're just crossing them off. The most common one you're going to see, though, is CH2Cl2, which is dichloromethane. In other words, just to make it simpler, if you don't see water or alcohol as your solvent, cross the solvent off. So the steps for solving the problem are exactly the same as before. That's one thing I tried to build something consistent that we can just keep adding a little bit to as the chapters go along, but it's not new processes every time. So your first step is going to be to list and label the reactants. So you have the 2-methylbutanene as one reactant and then the bromine. I've listed the 2-methylbutanene twice. One way is showing it the way that you have been drawing it all along. The other way is kind of showing it flattened out so you can kind of see the stereochemistry. So it's kind of whichever one is going to be better for you. And maybe you need to write it the way that we've always been writing it, the way on top, shown on top there, so that you can figure out what it looks like. The only reason why I would think that this might be worth the extra step to write it out the way that it's shown is because if you're reacting with a tertiary carbon like we're going to do in this reaction, and you have to add from the opposite side, having the CH3 group there might make you think that it's blocked, and so you can't react there. That's the only thing I'm thinking. It's the same exact kinds of labels as before, where you're looking for the incomplete valence shell, strained ring, pi bond, high concentrations, partial positives, negatives, crossing off hydrogens and carbons, and all of those steps. The most reactive feature is identified next, and that's the pi bond. So you're looking for something electron deficient. The thing that might bug you and that might take a while to get it in your head is that even though it's two bromine atoms attached to each other, and so there really isn't a positive and negative, you're going to induce a partial positive and negative as it approaches the pi bond, just because the electrons are going to run to the other side of the molecule. So I've got a partial positive and negative label there, even though it might bug you. Because you're reacting a pi bond, you want to know which carbon the electrons, pi bond electrons, are going to be pulled from, so it's good to label the primary, secondary, tertiary of the vinylic carbons. And then as your new little added feature that you're watching for, if what you're going to react with a pi bond has non-bonded electron pairs, then you want to note that, because that can be used to stabilize the developing carbocation. That's about the only new thing now for this whole deal. Once you've got everything identified, then use reaction mechanism arrows to show how the reaction occurs. And you're going to go from the electron-rich pi bond to the electron-deficient bromine. But then, as the carbocation starts to develop on the tertiary carbon, then you're going to additionally share the electron pairs with that so that it doesn't have to be a carbocation, because that's a stabilization trick. Okay, so I've got this drawn out both ways just in case you were going to go with one way or the other, but it's the same thing with the arrows either way, from the pi bond to the bromine atom, and then from the bromine electron pairs to the developing carbocation to form the little string ring. In addition, then, the bromine has to let go of something because it's forming two new bonds, so it's going to let go of one. So you're letting go of the other bromine atom. Okay, step 3 is always consider whether you have the option for a shift. But because the bromine has its electron pair there, you don't have an empty p orbital. And so you don't have any possibility for a shift anytime you form a strained ring intermediate. That's the purpose of putting something like mercury in, for instance, is to react it without allowing a shift to occur. Now you look at the mayhem that you created and see if it's okay to leave it like that. But no, you've got a strained ring, so you can't just go with that. So you need to list and label the reactive molecule plus any resources that you have to take care of it. In the first step, you used up the bromine, but you created a bromide ion. So that's your other resource that you have.
Question.
Uh-huh.
When the bromines break, do they end up with the split of it? They don't end up with the split number of electrons, right? One of them ends up with 8.
Great question. Yeah, the whole bond breaks and it's sent towards the bromine that is more, the more negative.
Okay.
Mm-hmm.
So then does it only have 6? Does it become a carbobromide? Or no, that's not right, a bromine cation or
So
whatever it is?
this has 6, except for you're also picking up 2 from this bond. And so that'll have 8, and that's why you're sending the whole bond over here too,
Okay.
just because you didn't want to have 9 on here.
I forgot about the bond over there. It's being used. That's right.
Yeah, it's a good question. All right, so you have the strained ring is the most reactive feature. That's driving the reaction. So what you need to find, and maybe I should add this in, a carbocation or a strained ring. You're looking for something with a non-bonded electron pair so that you can form a new bond. That will open up the ring. And you want the highest concentration because it's so reactive that it's going to react with pretty much anything it runs into with a non-bonded electron pair. The carbons on it are because, I was bad, I didn't put that in. Bromine is more electronegative, and so it's going to be pulling electrons away from the carbons. It's important to note the type of carbon each is that you could potentially react with, because just like before, you're going to follow stability of a carbocation. This time it's the stability of a developing carbocation. In addition, the tertiary carbon has a weaker claim to the bond, to bromine, and so that's where you're going to break the bond. This time it doesn't matter because you end up with a bromine on each carbon, but it could make a difference for some of these reactions. So it's good to think in those terms right from the start. As the bromine adds onto the carbon is able to let go of the bond to the other bromine in the strained ring, and so that's why it's going to open up the ring and take care of the issue.
And it's forming to that carbon because it's a better carbocation.
Mm-hmm. Better developing carbocation. Then once you have your product, evaluate the stereochemistry of it. There's only one chirality center that was created as a result of the reaction, so it's R and S. If there would have been 2 chirality centers, then you would have noted that you had a strained ring in the middle and you would have done cis and erythro.
Could you repeat that last bit? You would have done cis and erythro when?
If you would have had 2 chirality centers created as a result of the reaction. I know you're kind of iffy, but not only did you have training wheels here, but Mom was holding the bike besides. So now Mom's going to let go of the bike and let you try it on your own with the training wheels. I know it'll be a little struggle, but that's how you're going to learn it. All right. Z-butene with bromine in water. How expensive are these Apple pencils? How expensive are the Apple pencils?
Oh, like $50. It's like a style. They're fancy stylus.
Yeah, I guess because it has all the Bluetooth electronics and stuff on it.
Probably the battery, honestly. The battery just
Yeah.
charges like super fast.
The next problem or the next step? I'm probably going to switch over to showing you one more reaction. Looks like you're pretty much there. Okay, so when you're labeling everything, the pi bond's the reactive feature. The hydrogens are crossed off, though you can't react with them because the bond is too strong. The bromine is your, by default, the thing that you can react with. It has a non-bonded electron pair, so it tells you it's going to form a strained ring. The pi bond, and both carbons are secondary, so you could react with either one. The molecule's symmetrical, and so this time you don't have to draw out both products because they would be the same. So the pi bond opens up to react with the bromine. The bromine simultaneously shares its electron pair with the developing carbocation as a stabilization resource. You can't have a shift because it's a strained ring. But because it's a strained ring, you can't stop there. So you list and label all of the reactants that are left over. So you created a bromide ion and you have the unreacted water. Because it's a strained ring, it's highly reactive, and so the important feature is that the water is present in a high concentration. You could react with either carbon. It'll make the same molecule either way. And once it adds on, you can drop off one of the hydrogens. Because a strained ring is a similar idea to a carbocation where it's so highly reactive that it will react with anything it runs into first that has a non-bonded electron pair, and so the probability is it will run into water first because it's present in a significantly higher concentration. Mm-hmm. So that's why I said on the last go-around, maybe this is something I should fix here. Now you can think of carbocation or a strained ring. You're looking for the nucleophile at the highest concentration. That's the important factor. Mm-hmm. So when that adds on, you have two chirality centers that were created. Because you have two chirality centers, you have to think back over the mechanism, and you also use cis and erythro. There was an anti-mechanism, though, because the strained ring blocked one side, so the water had to add from the opposite side. The bromine blocked one side, so the water had to add from the opposite side, which is the definition for an anti-mechanism. And you started out with Z. So that one isn't changed. Sin is changed to anti, so that tells you it would be a 3O pair. A sin mechanism is the one reaction, and I'm going to see if I can get to it today.
Okay.
Yeah. All you know so far are the anti-mechanisms, which is anytime you have a strained ring like that, it has to be anti.
I don't know if it's cis or D.
It should say at the beginning of the problem, and if it didn't, then there's no way to tell what the stereochemistry would be. All right, so now you see the pattern, at least, for analyzing any of these reactions. And I think at this point, now that you've got a pattern written in your notes, then you can, then you just mostly need some more practice. I'll give you some practice for homework. That's how much I love you. Yeah, I know. Stop loving you so much. I know. Sometimes I say that to God, too. Please stop loving me. I can't take this love anymore. Okay,